My name is Hema Karunadasa, and I'm an assistant professor here at Stanford in chemistry. I've been around for 4 years now at Stanford. This is my 4th year. And I'm a synthetic chemist, so we make stuff. And over the past few years, my group has been exploring new routes to hybrid materials with an emphasis on hybrid perovskites. And I will tell you a lot about perovskites today. So we have been looking at hybrid perovskites for various different applications. But for today's talk, I will focus on perovskites we've developed as absorbers in solar cells. And if you're curious about other applications of perovskites, we can certainly talk about those after my talk. So perovskites belong to a very large family of compounds with very different structures, from 3D materials to 2D materials, 1D materials, zero-dimensional materials. And these materials have been known for a very, very long time. These minerals have been known since at least the 1800s. And by far, the vast majority of perovskites are metal oxides. So when I was an undergraduate, my first chemistry research project was to synthesize metal oxide perovskites. And I think it's fair to say that perovskites pulled me into chemistry. So I'm very fond of these materials. That's a great background. Okay. Thank you. So I remember synthesizing these metal oxide perovskites as an undergrad, and these require very high temperatures. So I would take the precursor materials, the metal oxides, grind it up in a mortar and pestle, form a very fine mixture, and shove it into a furnace. And I would heat these materials at about 1500 degrees, and 3 to 4 days after, I would get my perovskite, if I was lucky. And I think that high temperature synthesis is pretty awesome. I really loved using these big furnaces and high temperatures. I felt very macho making these perovskites. But it is still true that this particular synthetic method precludes the use of any kind of organic group. We can certainly put organic materials into a furnace and heat it at 1500 degrees, but the product wouldn't be quite as exciting, right? So in contrast to metal oxide perovskites, metal halide perovskites form in solution under ambient conditions, room temperature, room pressure, in solution. So we can use organic solvents, we can use water. So these much milder synthetic conditions allows us to incorporate organic molecules so that we can design these hybrids that have the properties of both extended inorganic frameworks as well as discrete organic molecules. So the perovskite structure is shown here. We get this inorganic framework consisting of corner-sharing metal halide octahedra. The framework has a negative charge. So to balance that charge, you will find positive cations sitting in these cavities defined by 8 adjacent octahedra. In the case where this cation is an inorganic ion like cesium, rubidium, potassium, this would be your standard inorganic perovskite. But in the case where this A-side cation is a small organic molecule like methylammonium, we call these organic-inorganic hybrid perovskites. And strictly speaking, methylammonium has carbon-hydrogen bonds. It's an organic molecule. But most organic chemists will tell you that methylammonium barely qualifies as an organic molecule. And we would love to put more structurally diverse, functional, more interesting organic molecules into these structures. However, we are really limited by the size of this cavity. And to put more exciting organic molecules into this structure, we want more space. So to get that greater degree of freedom, we also work with the related 2-dimensional perovskites, which looks like the 3D material has been sliced. But we still get to play with the cool photophysical properties of these extended inorganic sheets. But now, at least along 1 dimension, we have more space. We can put more structural, functional diversity into these materials. And my favorite aspect of hybrid perovskites is how they are synthesized. We form these materials through solution state self-assembly, which is a fancy word for saying that we just throw the molecules and the ions into solution. So in solution, you can imagine there's this giant free-for-all with organic molecules and inorganic ions tumbling around in solution. And what we do is we tune the crystallization conditions. So we can modify temperature, pressure, organic solvents, and so on. And if we get those crystallization conditions just right, we can get this mess to form these beautiful ordered structures where sometimes the inorganic sheets will template unusual architectures in the organic layers as well. And with respect to any kind of material that is technologically important, solution state deposition is greatly desirable, because this means that we can use very simple techniques for depositing films like spin coating, drop casting, and we can cover very large areas with this material. So the synthesis is extremely scalable and quite inexpensive. So the material that has caused a great stir in the photovoltaics community is shown here. This is a 3-dimensional lead iodide perovskite, and it's a hybrid perovskite because the A site cation is this organic molecule, methylammonium. This material was first crystallographically characterized in 1978, and in 2009, this material was shown to perform as a pretty good absorber in a solar cell. So the basic idea behind a solar cell is that we use a material as an absorber. This is a semiconductor with a band gap that is suitable for being excited by sunlight. So photons will hit this material, eject an electron from my filled valence band to my empty conduction band, and then we want to separate that electron and hole so that we can produce photocurrent. So we push that electron to the electron conductor, hole to the hole conductor, and this energy gap dictates the maximum voltage we can obtain from this solar cell device. So let me tell you why this material has caused such excitement as a solar cell absorber. I'll talk briefly about the strengths of this material. So for one, as I mentioned previously, it is extremely inexpensive to deposit even very large area coatings of this material. The precursors are cheap, and the film deposition methods are extremely inexpensive. Secondly, the lead iodide perovskite has a band gap that is almost perfect to use as a single junction absorber, as an absorber in a single junction solar cell, so a solar cell containing one absorber layer. But by adding bromide to that lead iodide lattice, we can change the band gap. The more bromide we add to the material, the larger my band gap gets. And these mixed halide iodide bromide perovskites have close to ideal band gaps to use as the higher band gap absorber in a dual absorber tandem device. So tandem solar cells can, at least in principle, reach higher efficiencies than single junction absorbers. And the fact that you can tune in a band gap so easily is actually a huge advantage. Thirdly, when we excite this material with light and we generate electrons and holes, those electrons and holes hang around for a very long time before they recombine. And the longer they hang around as free carriers, the more likely it is that the electron and the hole will find their respective charge transport materials, and we can produce more photocurrent in a device. So we monitor this by looking at PL decay time. So this is how quickly the photoluminescence dies. And we see these very long-lived components for methylammonium lead iodide single crystals. The lifetime here is about 1 microsecond, which means when we generate electrons and holes, they hang around for about 1 microsecond. So that's a very long time. And what's particularly impressive is that this is data obtained from this reference for a single crystal, but you can also get 1 microsecond carrier recombination lifetimes even in films. And films have much more defects, surfaces, grain boundaries than a single crystal. And that tells us that, well, there must be defects in the films, but those defects don't adversely affect the absorber, which is quite special. So for these 3 reasons and many more that I haven't listed, because this talk is not about the advantages of perovskites, the efficiencies of devices employing perovskites have just skyrocketed. So the initial demonstration was in 2009, and this was a very decent initial efficiency of 4%. But in just 6 years, the device efficiencies have climbed to 20%, which is now commercially viable. So this is incredibly exciting, and I'm a huge fan of perovskites. I would love to see this technology succeed. But it's precisely for those reasons that in my group we have chosen to focus on all the problems with this material, because we want to identify these problems and as synthetic chemists try to design materials that address those issues. So if you want to hear a talk about the strengths of perovskites, and there are many, these are remarkable materials, I can guide you elsewhere. But for the rest of the talk, I will talk only about what we think are the problems with these materials, and I will discuss some of our attempts at trying to address those issues. I will also point out that throughout this increase in efficiencies, the synthetic chemistry has not played a huge role. We have certainly changed small components of the lattice, changed, maybe thrown in some different halides, changed an A site cation, but the material has not substantially changed over these years. And the increases in efficiencies have been primarily due to better device fabrication methods, better encapsulation methods. So there's really an opportunity for synthetic chemists to jump on board now. So these are what we've identified as potential problems in this material. This material is not stable to moisture, not even ambient humidity. We can make nice black films of the 3D perovskite and just leave it sitting on our lab benches. Within just a few days, we see yellow spots forming on the black film. It's bad news when your black solar cell absorber turns yellow, because that means it's not absorbing sunlight. So the black film absorbs all this light, but the yellow film will only absorb this much light. And the rate at which this film decomposes to the yellow lead iodide depends on the quality of the film, but eventually it will degrade. So this is certainly a problem, and this means that during device manufacture and during device operation, we must block out water. And this can be done. It's not that hard to keep out water. It just means that manufacture costs will be higher than you might think with just the solution state deposition methods. A bigger problem in my mind is that not only is this material a source of lead ions, which are well known to be extremely toxic to human health, but this material is a water-soluble source of lead, which means that if the encapsulation in your solar cell is compromised at any point, with the next rainfall, we're going to have lead iodide leaching out of our roofs. And lead iodide is water soluble. It can easily contaminate the waterways, and it'll be hard to contain the material. So for example, cadmium in current solar cells is about 10 times more toxic than lead, but the cadmium source here is not water soluble, so the lead iodide is more of a problem. So here again, material encapsulation can help, but then the encapsulation has to be very good and reliable. And there's still some concern about using lead. There are some people who say we've spent the past few decades removing lead from our buildings. We are not going to paint our roofs with a water-soluble source of lead. So it is certainly a concern. The third point is kind of interesting, surprising really. I mentioned to you that we can throw bromide into the lead iodide lattice, and the more bromide I add, the higher my band gap gets. That's true. I can change my band gap very systematically by adding bromide. But you'd think that if the band gap was getting higher and higher, we should be able to get higher and higher voltages out of these materials containing more bromide. But these higher voltages have been very difficult to realize in these materials. So the lead iodide has a small band gap and gives a lower voltage. The lead bromide has the larger band gap, gives a higher voltage. And in between, we can really tune the band gap from 1.7 to 2.2 eV, but the voltages we get are quite similar to the iodide perovskite. So that's intriguing. If my band gap is changing, why is my voltage not changing? And I do need these higher voltages for tandem devices, so this is a problem that has to be fixed. So for the rest of the talk, I will just flesh this out more, but these are the three main points that I'd like to address. So as a synthetic chemist, we look at this structure and we ask the question, how can I impart more moisture stability into this material? Well, if you want to maintain the cool photophysical properties of the perovskite, you want to maintain the spatial extension of this inorganic lattice, and you really don't have much choice. You can replace one small organic cation with another, but as I mentioned, this cavity really restricts what we can do. Methyl ammonium is extremely hygroscopic, and we would love to replace this with a molecule that doesn't love water quite as much, but we just don't have too much choice. So here we decided to take a step back and view the broader family of hybrid perovskites. So I mentioned that we can form these 2D perovskites that look like the 3D material has been sliced. In the case where that slice has just a single metal halide octahedral layer, these are called N=1 perovskites. They have large band gaps, and they have very large exciton binding energies, meaning that when you hit the material with light, you generate an electron and a hole, and that electron and hole really very strongly feel each other, and it's very hard to separate that electron and hole. So this large band gap and this large exciton binding energy is precisely what you want to avoid in a solar cell, because you want a small band gap so you can be excited by sunlight. You want weak exciton binding energy so that the carriers can be split to generate photocurrent. So if I were to call this N=1, I would have to call the 3D perovskite N=infinity, and you can see here the photophysical properties are much better suited for PV applications. The band gap is smaller, the exciton binding energy is weaker than room temperature, meaning that there are free carriers at room temperature. But you might guess from the way that I have positioned these structures, these are just two extremes in what is really a continuum. And we can access these intermediate perovskites by using a mixture of both small and large cations. So the N equals 2 perovskite was crystallized in the 1990s. And you can see that the band gap drops a little bit, the exciton binding energy drops a little bit. And we were able to crystallize the first N equals 3 lead iodide perovskite. And you can see this nice trend. As the sheets get thicker and thicker, it starts behaving like a 3D perovskite. So the band gap goes down, the exciton binding energy goes down. And we felt like these values were suitable to evaluate as a solar cell absorber. Ian Smith formed this material by using a mixture of small and large cations. So the small cations go into these smaller cavities. The large cations go between these sheets. And he crystallized this beautiful structure that really looks like we have cut ourselves a more generous slice of that 3D perovskite. Ian then fabricated solar cells with this material. So he slapped on a hole transport material and an electron transport material with the perovskite in between. And his initial solar cells created with this material had efficiencies of about 4.7%. So when we published this result, 3D perovskites had efficiencies of about twice this value. We certainly didn't attempt to optimize our devices. We weren't trying to go after efficiencies. But we were motivated to show that this 2D perovskite can bring new properties that the 3D perovskite cannot show. So this is what we investigated, and these are some of the things we found. The material has a larger band gap than your 3D perovskite, so you can get higher voltages out of this material. 2D materials form plates when they crystallize because crystallization along the AB axis occurs much more rapidly than perpendicular to that direction. And this very reason allows the material to form nice continuous films. So we can simply drop cast this material onto a substrate, and it coats the substrate very uniformly. We don't even have to anneal these materials. It forms a nice film. In perovskite devices, material morphology is everything. So a nice film is very important. In contrast, the 3D perovskite, because it doesn't have this preferential orientation, requires a lot more loving care to form a nice continuous film. But the greatest advantage of the 2D perovskite is moisture resistance. So with the 3D perovskite, when we expose a film to 55% relative humidity, we are monitoring the decomposition of this material using powder X-ray diffraction. And we see that there are decomposition products emerging at around 4 days. After 46 days, we only see peaks in the powder patterns corresponding to PbI2, lead iodide. So the material is completely degraded. But the 2D perovskite exposed to the same conditions shows no change with respect to the powder pattern. This material is a lot more stable to moisture. And even the devices I showed you were fabricated under ambient humidity, whereas you cannot do that with the 3D material. But to us, the most exciting aspect of the 2D perovskite is its tunability. As I mentioned, there isn't much you can do with the 3D perovskite unless you start changing the metal. But now we have both the organic layers and the inorganic layers to mess with, and there are lots of things we can do. So for example, with the inorganic layers, you could imagine changing the number of the sheets. Here we wanted a well-defined structure, so we crystallized N equals 3, but there's no reason to have a well-defined structure in a device. And you can start increasing the thickness of these sheets. We can change the connectivity of the sheets. So instead of slicing this way, we can slice in a different orientation. And of course, we can change the metal and the halides. And in this work, we proposed that if you were to use a different ratio of small to large cations, we can form not single-phased, but mixtures of materials with larger values of N, and that these materials should have lower band gaps and higher carrier mobility. And very recently, using small and large cations, these groups have shown that you indeed can achieve the higher efficiencies with 2D perovskite devices. But now the organic layers is a whole new playing ground for synthetic chemists. You could imagine putting even more hydrophobic molecules that really repel moisture. So this is like taking the 3D perovskite, slicing it very, very finely, and coating it with a hydrophobic layer. You could imagine putting organic photosensitizers, molecules that absorb light, so that the fraction of the solar spectrum that is not absorbed by the inorganic sheets can be absorbed by the organic layers. And you could even imagine conductive molecules that transport the charge generated in the inorganic layers. So there are lots of things to do with this new platform, and we are engaged in all of these. And there could still be things we haven't thought about. But the fact remains that if you throw the 2D perovskite into a bucket of water, it will decompose. So we didn't make it moisture waterproof. We just gave it some more time. We made it a little more moisture resistant. So it's still a concern that the material degrades to PbI2, and PbI2 is water soluble. So what we would love to do is get the lead out of the perovskite, find a different material that behaves like the lead perovskites that does not contain lead, and preferably nothing more toxic than lead. So if you take a look at the band structure of the lead iodide perovskites, you see that the valence band, the top of the valence band, has predominantly lead 6s character mixed in with halide p character. The bottom of our conduction band has lead 6p character. And to date, there have been lots of work on this, but to date, we don't really know why the lead halide perovskites are so good. We just know that they are. So the simplest thing that we can do to find a functional analog is to try and mimic this electronic structure as closely as possible. It's not a very educated step, but it's a practical step. We don't know why it works, but we know it works, therefore we'll match it. So to do this, we can certainly look at metals that have the same electronic configuration as lead. And this is what chemists do. We grab a periodic table and we say these are the metals that will act like lead. We all did this in general chemistry, right? So you can pull your periodic table up and say everything along this column should behave like lead. So let's go up, let's go down. Well, assuming you don't want to create more problems, you probably don't want to go down. These materials are radioactive. But you can go up, except that you can't really go up because germanium and tin 2+ states are extremely unstable and will very easily get oxidized to tin 4 and germanium 4. If you're interested in why tin and germanium behave differently from lead, just ask me after my talk. But these materials are oxygen sensitive, these materials are radioactive, so we cannot go up and down. We can go left and right. So thallium 1, lead 2, bismuth 3+, all have the same electronic configuration, but thallium is more toxic than lead, therefore bismuth is our natural choice. And in fact, we were not the first to decide this. Bismuth has been used for decades as a non-toxic replacement for lead in very different applications, from medicine all the way to ammunition materials. So there's been a movement to replace lead in bullets with bismuth to reduce their toxicity. Here, the toxicity is not for the animal getting shot by the bullet. Bismuth bullets are as lethal as lead bullets. It's for someone eating that meat. I had to explain that I feel silly talking about non-toxic bullets. But bismuth is still the people's choice, except that bismuth, to get the same electronic configuration as lead 2+, we need bismuth 3+. And we have to deal with this difference in charge. So if you had one single lead metal surrounded by 6 iodides, that lead feels a negative charge of 4-. And that's a lot of charge for that 2+ metal to bear. And that's one of the reasons why lead iodide shares those iodides and forms these extended structures. Bismuth has a charge of 3+, so it has less reason to share its halides. And as a consequence, most bismuth halide structures we find are lower dimensional analogues of the lead 3D perovskites. So we find 0-dimensional structures, 1D chains, 2D sheets. It's hard to find a bismuth halide with 3D connectivity. Related to that is the problem that if we did want to put bismuth into this perovskite structure and we had no intention of changing A or X, we are really faced with the problem of how do you put a 3+ cation into a 2+ site. So here also, we took a step back and looked at the broader family of perovskites and realized that we should double the unit cell. So instead of working with ABX3, we can look at double perovskites that have the formula of A2, B2, X6. Now, it is still true that the 2 B sites have to give us a net charge of 4+, but that can be shared equally or unequally between the 2 B sites. And this gives us the double perovskite structure, where here I show you an ordered double perovskite where the B and B prime sites will alternate in all 3 dimensions. So now instead of 2+ and 2+, I could have 1+ and 3+. So if I found the correct 1+ cation, I could put bismuth 3+ into this lattice. And Adam Slavny found that silver 1+ is ideally suited for going into a a double perovskite with bismuth 3+, and he crystallized this beautiful ordered double perovskite with silver and bismuth alternating in the lattice. He can grow these very large, beautiful crystals. These are truncated octahedra. They reflect the symmetry of the space group of the material. And this is a cubic structure. But if you were to look only at the bismuth atoms and join those and find the bismuth sublattice, you find edge-sharing triangles. So it's kind of neat that in double perovskites, there's a triangular lattice hiding inside a cube. Adam evaluated this material as a solar cell absorber, and he found that the material has an indirect band gap of 1.95 eV. So 1.9 eV is actually quite good as the higher band gap absorber in a tandem solar cell device. The indirect band gap is initially not so great. With a direct band gap material, you get a much sharper absorption onset here, and an indirect band gap simply means that less sunlight is absorbed at that band gap onset compared to a direct band gap material. However, silicon is an indirect band gap material, and we all know that silicon works very well in a solar cell. And the reason for that is when you have an indirect band gap material, all you really need to do is get a thicker absorber layer so that more light is absorbed at that band gap onset. The problem with using a thicker absorber material is that when the carriers have to move across a thicker absorber layer, they are more likely to recombine. So you need a very long carrier recombination lifetime to get away with that thicker absorber layer. Silicon has such a very long lifetime. So we looked at the recombination lifetime for this 2D perovskite, not 2D, double perovskite. And Adam finds that this material also has a very long-lived PL component. We see an initial very fast decay component, which has also been seen in the lead perovskites, and this has been related to recombination as surface sites and defect sites. And we say that because we see a lot less of it in single crystals compared to powders. So this is a single crystal, and this is a powder. But we also see this very long-lived recombination process that doesn't change significantly between crystals and powders. And this is, we still need to do a lot more work to really figure out the origins of this fast decay and slow decay, but this is very promising because it tells us that there is this very slow recombination process, meaning that carriers can hang around for long enough and navigate through that thicker absorber layer that is required for this material to generate photocurrent in a solar cell. We also looked at stability, because stability is a problem with these lead perovskites. We can expose this material to light for 30 days. This is an important experiment because silver halides are notoriously light sensitive. This is the basis of photography. Silver bromides decompose in light. But during this 30-day exposure to light under nitrogen, we saw no decomposition. We did see some surface discoloration, so we need to do longer stability tests. This material is completely stable to humidity. And we also looked at heat. So it's rather surprising that the lead halide hybrid perovskites are extremely unstable to heat. So even if we heat the material at 60 degrees for 3 days in air, the material decomposes. This is the lead iodide perovskite. This in blue is the lead bromide perovskite. All these peaks correspond to the lead halides, PBBr2, PBI2. So 60 degrees is not very hot. Your standard solar cell reaches 80 degrees routinely. When we manufacture these devices, we often will anneal at 100 degrees Celsius. So built-in thermal stability is very important for solar cell absorbers, and this material, because it's completely inorganic, can be heated at 100 degrees for 3 days without any change. So here also, I think the most exciting aspect of this material is its tunability. There's been a great deal of interest in forming less toxic materials with this structure, but the ABX3 structure has really been restrictive for replacing the B site with stable and non-toxic metals. But the double perovskite structure really relaxes that requirement, and we can put many more combinations of metals in very different oxidation states, and the playing field is now wide open. And our preliminary photophysical studies have been very promising, and we've got this glimpse that the material actually can have the very long carrier recombination lifetimes, the defect tolerance we see in lead perovskites, and this work really motivates further studying optical properties of double perovskites. I should also point out that just 2 days after we published this work, the same material was reported completely independently from another group. So the last point I wanted to tell you was this very curious occurrence that we saw in mixed halide perovskites. And this is work done in collaboration with Mike McGee's group. So I mentioned you can throw bromide into the lead iodide lattice and we can dial in a band gap, which is very cool. And if you can change the band gap, that means we should be able to change the voltage of the material when we use it in a device, and we should be able to get an idea of that voltage by looking at the photoluminescence energy. So a material that can give a higher voltage should give higher energy photoluminescence. So we can look at the photoluminescence of these films and we see that it tracks with bromide content. So lead iodide films with a smaller band gap have lower energy photoluminescence bands. The bromide with a larger band gap has higher energy photoluminescence. But you'll also notice that even though there's this nice trend, some of these curves look like hell. And these are not bad data. These are changing data. So the material is evolving with time, and that's why these curves look so nasty. So Eric found that if he continuously exposed these mixed halide perovskites to light, the material begins to change. And he tracked these changes. So what he finds is that for the x equals 0.4 mixed halide perovskites, this is the formula, you would expect a photoluminescence to come up at this energy, and initially at time equals 0. That's exactly where we get the photoluminescence. But if he continues to expose this film to just one sunlight for just 1 minute, this PL band begins to decrease in energy, and a new band forms that gets more and more intense with light soaking. And this is true for every mixed halide perovskite. Even though the initial PL tracks with the band gap, all of these intermediate PL bands converge right here. So the all bromide doesn't move, the all iodide doesn't move, but the mixed halide perovskites all move to give this same low energy PL. And that was very curious. So we wanted to check whether the material changes during this process. So Eric did a very high-tech experiment. He grabbed his bicycle light and he suspended it inside the powder diffractometer such that the light was hanging directly below the perovskite film. And he took a powder pattern of the perovskite film in the dark, and then he turned on his light and took a powder pattern again. And he finds that every reflection in the powder pattern in the dark splits into 2 reflections when the material is illuminated. And if we assume that the material isn't changing dramatically during this process, it suggests that we are making a material with a larger unit cell, larger d-spacing, and smaller d-spacing. But what is really curious about this is every change I told you about, the PL shift, the change in the powder patterns, they are all completely reversible. So in the dark, the material goes back. So under illumination, the material changes, and we get low energy PL. When we rest the material in the dark, everything goes back. So that was all very curious. So compiling all the data I showed you and some data that I didn't show you, we came up with a proposal of what might be happening in this material. So this is my valence band of my lead halide perovskite. If you look at the top of the valence band, you essentially see halide p orbitals. So if I generate holes in this material, that hole is at a halide. I know that when I irradiate this material, my PL energy moves to lower energy. So I know I am accessing some kind of trap state, which has lower energy than my initial state. So our proposal, our hypothesis, is that we initially have this mixed halide alloy, where there's a nice mixture of iodide and bromide, but under illumination, the material segregates, and we get iodide-rich domains and bromide-rich domains. And one reason this might happen is simply due to the energy of the holes. So if you were a hole, you would be more stable in an iodide compared to a bromide. So you could imagine that all the holes migrate to the iodides. And this might serve as a driving force for more iodides to segregate from iodide-rich domains that can really stabilize those holes. Or there could also be a thermodynamic driving force for halide segregation under illumination. And if ever you have a case where you have both a small band gap material and a large band gap material in electronic contact, you will only get PL photoluminescence from the lower band gap materials, because all the carriers funnel to the lower band gap material. So essentially, the bromide-rich domains in this material are PL silent, and we only see the PL from that lower band gap lead iodide material, which means that no matter how much bromide you put into this material, if this continues to occur, you will never get high voltages, because your voltage is only dictated by that iodide-rich region in your film. So everything we've seen so far, this is still just a hypothesis, but everything we've seen so far is consistent with this hypothesis. And this tells us that even though you can change the band gap, you really cannot change the voltages you can obtain from these materials. But there is hope. Recent studies have shown that material composition can change this halide migration effect or this trap formation, and material morphology can also mitigate this effect. Studies have shown that if you make nicer and nicer films with reduced grain boundaries, you get less of this redshift. And this makes sense, because we would expect halide migration at grain boundaries to be very different from ion migration in the bulk. So our proposal for halide segregation requires halides to move. So we reasoned that if we were to really squish this lattice, really compress this lattice by pressing very hard, we should be able to change either the kinetics or the thermodynamics of this phenomenon. So we have a collaboration with Wendy Mao. She studies materials under extreme environments, and she can press very hard using a diamond anvil cells. So Adam and you got the first single crystal structures of hybrid perovskites under pressure. So we can figure out exactly where the atoms are in the high pressure phase. And they find that in both cases, you get the same high pressure structure. If you like crystallography, the space group is IM3 bar. And then Adam put these mixed halide perovskites into a diamond anvil cell so that he can change the pressure at which we are pushing against this material. And he looked at photoluminescence as a function of light soaking. So we can monitor how the photoluminescence changes as a function of time and also as a function of pressure. So we find that close to ambient pressure, we still get this PL redshift as we would expect. However, as we increase the pressure, the steady state PL energy we get gets higher and higher. And this is great news, because these are not very high pressures. And this essentially tells us that if we press this material really hard in a solar cell, we can obtain higher voltages from this material. We still do see that the redshift, but it is reduced. But so here I think we are within technologically reasonable pressures, but that's no reason why we shouldn't press any harder. So we continued pressing this material, and we find that at even higher pressures, we start seeing a second peak, peak 2. And this peak does not shift with light soaking. It shifts with pressure, but it doesn't change as a function of illumination time. And at still higher pressures, peak 2 dominates over peak 1. And studying the way that peak 2 changes as a function of pressure, we see that it behaves the same way you would expect the material to behave if you didn't get this weird halide segregation. So we think peak 2 is from the native material where halide segregation is suppressed. And this is exactly where we would love to be in a working solar cell device. Yes?
These materials exhibit a piezoelectric effect?
Piezoelectric effect. We haven't looked for it, but there have been so many studies on these materials that I wouldn't exclude it. Do you mean specifically mixed halide perovskites?
In general.
Yeah, they have looked at piezoelectric effects in 2D perovskites. And yeah, I'm not sure. We certainly have not looked. So pressures above 1 GPa are probably not practical to apply in a photovoltaic device, but there are different ways that you can access pressure. So certainly you can squeeze the material. But there's also ways of exerting chemical pressure. So this is done by adding very large cations into your lattice that don't quite comfortably fit with respect to its nearest neighbors, so it pushes its neighbors away. And theoretical studies have shown that kind of chemical pressure you exert can really mimic the properties of mechanical compression. So if we can figure out a way to chemically stabilize that high pressure phase we wouldn't have, we think that we can suppress the halide migration. That would be pretty exciting. So I will end. Very basically, hybrid perovskite, I don't want to imply that these materials only have problems. I have only focused on its problems in this talk. These materials are truly remarkable absorbers, and they're currently being considered for commercialization. But that is precisely why we should very critically look at these materials and ask how can we improve them. And everything I told you about could be at least partially mitigated by device engineering, device encapsulation. The question is will the encapsulation be good enough? But regardless of any of this, certainly it is true that if we can mimic the properties of the lead halide perovskites in a material which is more stable and certainly more environmentally benign, that would remove the major impediments towards the commercialization of this technology. That would be very exciting. And to me, as a synthetic chemist, this is a great challenge to try and figure out why these materials are so good. As we start making more and more analogues of these materials, we will actually perhaps understand overarching design principles that tell us that this particular structure yields this type of photophysical behavior. And it's certainly the time now to think about the next generation of absorbers and address some of the problems in these materials. So with that, my group has done all this work, and it's thanks to their hard work that I have these results to show you. They're sitting in a row right here. Ready to attack. I will accept questions from anyone except members in my group. And they have done a really great job exploring various aspects of hybrid perovskites. I only told you about PV applications, but we've looked at these materials for gas capture, for batteries, for phosphors. If you're interested in these applications, you can check out our website, and you can certainly come talk to us. Everything I told you about photovoltaics was sponsored by GCEP, and it's really been wonderful to have their support, as well as the Precot Center has supported all of our photophysical characterization of these materials. The more fundamental studies were supported by the Sloan Foundation and the National Science Foundation. Well, with that, I'll end. Thanks for listening, and I'm happy to take questions. I guess I'm moderating, so I'll now take questions. Ed?
How high efficiency do you get with the double perovskite to silver going?
Yeah, we have not yet made devices. It's actually been very hard to make nice films of the double perovskite, but we are going full force to make these films. And once we do that, we will incorporate it into a device. But right now, we don't know. That's our next target. Chris?
Hema, what's known about the oxides? What would you looked at changing the metals but keeping the charge the same? But if you went from, how much difference in radius is there between the iodide and the oxides?
Iodide is bigger. I think oxides and chlorides are a good match.
The oxide's about the same size as the chloride. So the problem then would be getting to this electronic structure in an air-stable metal.
Yeah.
You'd be...
So the perovskite oxides have been investigated mostly for photocatalysis. So those band gaps are pretty large. I think niobium oxide is the material. The perovskite has been studied quite a lot, but I think that's only excited with UV light. It would be great to, so oxide, the problem is oxygen is even more electronegative. So in the valence band, basically, if you go from iodide to chloride, your valence band goes down and down in energy, which means your band gap basically gets larger and larger. And chloride has the same electronegativity as oxide. So I would imagine that the oxides will have very large band gaps. But of course, it depends on the metal, so I wouldn't discount it. Yeah.
So you showed the PL will affected by the light soaking,
Yes.
right? In the real solar cell, you also have additional electrical field.
Yes.
Will that affect the segregation? Will that facilitate or inhibit segregation?
Yeah, so it turns out these materials are also ionic conductors. And a lot of very old studies have actually shown that these materials are halide conductors. And more recent papers have also shown that. So in an electric field, I would imagine there's halide mobility regardless of light soaking. You may not get the same segregation effect. As to the question whether if you both soaked it with light and applied a field, can you change it? We have seen changes in the way the material behaves, but we don't have a consistent explanation for that right now. Yes.
Do you have any data for substituting the methylammonium with fluoromethylammoniums?
Yeah, we tried that. Yeah, that's a good suggestion. It should work, right? Yeah.
There's a big difference between what you can, what reality may show.
Yeah, tell me about it.
So do you have any, can you share any results from that?
Sure, we tried, I think it's basically nasty chemistry. And at the end of the day, we realized you don't buy yourself that much by fluorinating the small organic. Monofluoromethylammonium is known, I think. We tried to make films. I think it was also, this was a while ago. This is the first thing we tried. And I think we couldn't form the perovskite. Certainly, it would be great to fluorinate even further, but then the molecule gets to be too large. I think the problem is we couldn't make a single-phase material, and it was very hard to make films of the material. As you start adding, fluorine chemistry is also very nasty, so it was very hard to convince one of my students to continue this. They have way too much freedom in my lab.
Well, good challenge for the synthesis chemist.
Yeah, but overall, I mean, we are fluorinating the larger groups now. And we have some recent work showing that that actually further increases the moisture stability. So I think it is a better strategy to just throw in larger cations, but not quite as much, so that we have larger sections that basically behave like a 3D perovskite.
I was also hoping that just if you could slightly increase the size of that cation, that you might get your pressure
Yeah, absolutely.
as well. So.
Absolutely, yeah.
My question is motivated by comparing perovskite traits with organic photovoltaic traits. And so I wanted to ask whether there were any materials that completely could do without any organic, without any organics involved, including in a device build-up where you might have maybe like an organic whole transport layer otherwise.
Certainly, you can make cesium lead perovskites, I think bromide and iodide perovskites, and they have been put into devices and they function. The efficiencies haven't been very high. I think the highest was probably like 4-5%.
All the way to the contacts.
With all the contacts, fully functional devices. There's a lot of interest in the cesium analog because the thermal instability of the material is very likely due to the volatile organics. Turns out that cesium lead iodide at room temperature, the stable phase is not a 3D perovskite, so you need to kinetically trap the material as a 3D perovskite. Cesium bromide is a perovskite, but it just doesn't perform as well. Yeah. It would be nice to get rid of methylammonium.
One last question, Hema, just because I knew about the cesium result, but I don't know whether anybody has made the mixed anions. In other words, large organic anions with cesium as the complementary. Sorry, large organic cations with cesium as the small organic cation. Small cation. So cesium, I don't know. One of your large cations.
To my knowledge, no. There are certainly 3D perovskites with mixed cesium and organic cation.
So that does make a perovskite phase.
A 3D perovskite, yes. Are you asking about 2D perovskite?
Yeah, these slices like your n=3.
Yes, to my knowledge, cesium has not gone into those perovskites.
You expect that using it's a slightly smaller cation, right, than methylammonium?
I think that's right.
So is there reason to believe that that would destabilize the perovskite structure in the 2D structure, or finite N structure?
Yeah. There's no reason that I can think of that it shouldn't work. Because these tolerance factors don't take into account like small deformations in the lattice, which actually are important. So yeah, I cannot think of any reason why cesium cannot go into the smaller site in the 3D structure. Okay, cool. Thank you very much.